Okay, here comes some notes about what we have been learning about. I'm trying to focus this. Maybe it's the paper that's out of focus, not the camera. So put on the glasses. All right, so what have these derivatives been telling us about functions? So that's what these notes are about. So the main thing about these notes is what is a first derivative good for and what is a second derivative good for? What does it tell us about a function? Because then we're going to be using derivatives to sketch functions, and we're vice versa, using functions to sketch derivatives. But actually it's really that you want to be able to take a derivative and sketch a function from it, because a derivative is actually an easy way to help you sketch a function when you don't have Desmos. Okay, so let's have a look. Stationary points. The stationary point of a function is a point where the derivative is equal to 0. Okay, so we know when the derivative is equal to 0, that means the slope is equal to 0. Okay, so the slope of f of x is 0. Okay, so when the derivative equals 0, that means the slope of f of x is 0, or rather, if I put that more completely, the slope of the tangent at a point on f of x is 0. Okay, so you can see that here in the picture. When the derivative is 0, you're going to have the derivative equal to 0. So right here, you have the derivative would be the slope of this tangent line. It would be equal to 0 right there. Okay, so right here, the tangent has a slope which is equal to 0. And what happens there? When that happens, we have a maximum or a minimum. So this point B, this happens to be a maximum. This is a local maximum. So point B is a local maximum. And the slope there is 0. Okay, and down here, again, the slope of the tangent is equal to 0. And what do we have here? We have a local minimum. Local minimum. Okay, so notice though it says we could have something else called a stationary inflection. What the heck is a stationary inflection? We're going to get back to that in a minute. Okay, so point A, where's point A? A is a global minimum, because notice this graph has restrictions. It doesn't go past -5 for x. So that's the lowest point on the graph, so we do get to call that a global minimum, even though if we didn't have the restriction, it would keep going down forever, in which case there would be no global minimum. But since the domain is restricted, this does have a global minimum, and it has a global maximum at point D, but only because the domain is restricted. If the domain had not been restricted, then there would be no global max and no global min, because these would have gone on forever. Okay, B and C are turning points where the shape is like this, where the curve has this shape, and the first derivative is equal to 0. The slope is 0 at that point. Okay, so we have our local maximum. So right here, when it's that shape, we have a local maximum, and this one, point C, we have our local minimum. Okay, so that's all should be familiar. We've been talking about this quite a bit lately. Right, so for many functions, the local maximum or minimum is also the global maximum or minimum. For example, y equals x squared, the point 0, 0 is a local minimum, but also a global minimum. So it's possible for something to be both a local and a global minimum at the same time. I'm not too worried about that. I'm just reading these out loud. Okay, so here comes the more interesting stuff. Stationary points of inflection. So up above here, we said if the derivative is equal to 0, three things could happen. You could have a maximum, a minimum, or a stationary inflection. So far, we've been talking about maximum, minimum. So what is a stationary inflection? Now, I want to go back to the packet. I want to go back to this packet, and I want to talk about question number 5. Question number 5, find the first and second derivative of x cubed. So if we find that, we get 3x squared, and the second derivative would be 6x. And then we can graph it. So here is my function, x cubed. And then if I graph on here the first derivative, so what was my color coding? Orange. So my f of x is this one, so let's keep track of that. And then my color I'm using pink. So then this one, 3x squared, well, that would be a parabola, and the vertex would be at 0, 0, and it has a vertical stretch of 3. So instead of over 1, up 1, it would be over 1, up 3. Again, you could have used Desmos to help you with this. So notice, this is my first derivative, and does it have an x-intercept? Does it have a, yes, there's my x-intercept. It has an x-intercept. So, from what we've learned, where we have an x-intercept, we should have a local minimum or maximum. But look what's happening on the function. It does not have a local minimum or maximum. It does, though, have a slope of 0, because you're coming up, positive slope, and then it gets more and more gentle, and then it kind of does this turn, but it keeps going up. So it turns, but instead of coming down like a parabola, it turns, but then it goes up. So in fact, the slope is 0 right here, okay? As it comes to 0, the original function, as it comes to 0, the slope is 0, but it's not a minimum, and it's not a maximum. This is called an inflection point. In this case, it's called a stationary inflection point. Stationary means it's not moving. The slope is 0. It has no speed. So its slope is 0. It has no speed. The speed is 0. The slope is 0. The speed is 0. So that's why it's called stationary. Stationary, you're not moving. You have no speed. But it's not a maximum or it's not a minimum. So that's what they're talking about here when they talk about a stationary inflection. So far we've only talked about maximums and minimums, local maxes and minimums, but there's something called a stationary inflection. So that's the next part of the notes. So, it is not always true that whenever we find the value of x where f prime of x, the derivative of the function, equals 0, we have a local maximum or minimum. And here's the example I just went over. F of x equals x cubed has a first derivative of 3x squared. And if we set that equal to 0, x is equal to 0, okay? So when 3x squared is equal to 0 is right here. And that is not a maximum or a minimum. This is called a stationary inflection, okay? So it is possible to have something other than a maximum or a minimum when the first derivative equals 0. So we're adding a little more vocabulary. So this point right here, the first derivative is equal to 0, but it is not a max or a min. It is not a max or a min. Instead, it is called a stationary inflection. So stationary means the slope is 0, okay? So stationary, not moving, means it's not moving. The speed or the slope is 0. Okay, stationary means it's not moving. The slope is 0. So that is a stationary inflection, and the first derivative equals 0 there. Okay, so this was the example that we had in our packet. So what is going on there? That's what we're kind of wondering. So here when I ask the question, what do we expect to find on f of x when the first derivative equals 0? We expect to find a maximum or a minimum, but it didn't happen on here. Oh my gosh, craziness. Instead, what we have is called a stationary inflection. Stationary inflection. Okay, what else does it say here? The x-axis is a tangent to the curve, which actually crosses over the curve at 0, 0. This tangent is horizontal, but 0, 0 is neither a local max nor a local min. Okay, that's a fancy way of saying what I just said right here. All right, so let's now take a look at the second derivative. What's going on with the second derivative? Okay, so that's talking about, instead of the first derivative only telling us about mins and maxes, when we set it equal to 0, we can also have something called a stationary inflection. All right, let's look at the next page. Shape. Okay, so there are some shapes. Here's the new vocabulary that I asked you to use on the packet today. When we have a curve, we can say that it's concave down. This is concave down, or we can say it's concave up. Okay, so notice here we have a function that is concave down, and here's the function y equals negative x squared. Okay, so let's go back to our packet and find where did we have y equals negative x squared. We had it right here. So y equals negative x squared. If we take the first derivative of that.
E.L. Soccer has an early dismissal of 2:55. Teacher, you can refer to your email for a roster. Again, E.L. Soccer has an early dismissal of 2:55, and you can refer to your email for a roster of students. Thank you.
All right. Sorry for the interruption. Let's keep going. So here our function x negative x squared, the first derivative would be negative 2x, and the second derivative is negative 2. Okay, so what I want you to notice here is that this is concave down. This one is concave down. This one was concave up. And then I want you to notice something about the second derivative. Second derivative was 2. Second derivative here is negative 2. So what does the second derivative tell us about the original function? If you haven't figured it out yet, it tells us about the shape. It tells us about the concavity. So it tells us whether something is concave up or concave down. So that's what the second derivative is good for. The second derivative can tell me if my part of my function is facing up or if it's facing down. Okay, and it doesn't have to be a parabola. It could be anything. If you look at the second derivative, you're going to see that relationship. The sign of the second derivative will tell you about the concavity, whether it's facing up or facing down. So, which begs the question, what happens when the second derivative equals 0? So if we go back to this one, where is it? This one. No, not that one. Yes, this one. When it equals 0. If I graph the second derivative here, so what did I do with my straight edge? There it is. My y-intercept is 0, and my slope is going to be positive 6. Over 1, up 6. Over 1, down 6. So if I graph my second derivative, here's my second derivative. When does the second derivative equal 0? Bam, right there. It equals 0 right there. And so to the right of that, my second derivative is positive. And now look at the values of the original function. Those were in orange. Look at the values of the original function here in orange. Notice this shape where my second derivative, so where my second derivative here is greater than 0, the shape of the original function is looking like that. That is concave up. But if you look to the other side, on this side, where my second derivative is negative, notice these values, my second derivative is negative. So when the second derivative is less than 0, look what's happening with this side. It's shaped like that. Okay? This is concave down. Concave down, and this is concave up. So if you didn't notice it on your own, here's what you should have noticed, that the second derivative, the values of the second derivative, the function values of the second derivative tell me the shape, the concavity of the original function. Crazy, huh? So what's going on then right here? What's going on where it equals 0? So that's where we have that stationary inflection point. So besides having a slope of 0, what else is going on there in this case? It's changing its shape from concave down to concave up. So the second derivative, when the second derivative equals 0, so when the second derivative equals 0, that's where we're going to have it change shape. It's going to change shape. Okay, so that's what's in this next set of notes, I think. Let's have a look. All right. So consider concave downwards. So if we have a concave down, notice here's the slope, positive, 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 negative, negative. So notice my slope values, 2, 1, 0, negative 1, negative 2. My slope values are going down. So my derivative is going to be decreasing. If this is my function, my derivative is going to be going down. It's going to be a line, a diagonal line, and it's going to be going down. The second derivative is going to be negative. And so the second derivative is going to be less than 0. See, it's concave down. This one, so, here it is right here, negative x squared. If we take the first derivative, So if we take the first derivative, we get negative 2x. Okay, so notice my slope is going down. And if we take the second derivative of that, we just get negative 2. And see how it's upside down? It's concave down. Okay, so here, first derivative is 2x. See how that's positive? My slopes are increasing. They're getting bigger and bigger as I go this way. But the second derivative is equal to 2. See how that's positive? It gives me a concave up curve. Okay, so second derivative tells me my concavity. All right, points of inflection. So on this one, we saw that we had the stationary inflection point. And that's because we had the first derivative equals 0 and the second derivative equals 0 there. That's when we have a stationary inflection. But it is possible to have an inflection point that's not stationary. So that's what we see here. It's possible to have a shape of a curve like this. So we can have an inflection, see where it's changing shape from concave down to concave up. So from here to here, I'm concave down, but on the other side, from here to here, I am concave up. And so right here at this point of inflection, the second derivative is going to be equal to 0. That's where it changes direction. When the second derivative equals 0, it's going to change direction. But notice the slope there is not 0. So in this case, the first derivative does not equal 0. In fact, for this particular one, since my slope is down, my first derivative here would actually be less than 0 because I have a negative slope. So for this particular example, I have a negative slope. Okay, not all functions are going to look like this. It could have gone the other way as well. Okay, but for this particular case, the first derivative would have a negative number here because my slope is negative, but the second derivative would be equal to 0 because right here it's changing shape. Second derivative tells me where it changes shape. Okay, this one, notice where it's changing shape. It's changing from concave up to concave down. Okay, so it's changing from concave up to concave down right here. And at this point of inflection, notice the slope is 0. The slope right there is equal to 0. So that means at this particular point, both the second derivative and the first derivative are going to equal 0 because the slope there is 0 and we have a change of shape. So the second derivative is equal to 0. Okay, so the second derivative is very handy for helping us sketch a function without Desmos. Okay, of course, if we have access to Desmos, who needs derivatives? But without Desmos, these derivatives are really helpful in helping to describe a function and what's going on with it. Okay, let's see. Did I want to say anything else on that particular piece of paper? I don't think so. I think moving on to the next one. Where was it? Oh, yes, the summary. Okay, the summary comes next. I want to make sure I haven't missed anything here. Anything else I wanted to add to that? No, I don't think so. Okay, so the summary, I love the summary page. Sorry that the Xeroxing came out really bad, and I really apologize for that. If you want to print it out again, if you have a color printer at home, I attached these documents to the assignment in Canvas so you could print it out in color, because this was actually printed in color, and then I put it on my copy machine, and then there was like ghosts from the page behind it. Sorry, it's just kind of a mess. But what I really like is I like this Venn diagram. So here, this says, in case you can't read it, the first derivative. When the first derivative equals 0, there's 3 things that could be happening. You could have a local maximum, a local minimum, or a stationary inflection point. Okay, so this is our nice little Venn diagram. If the first derivative is equal to 0, 3 things could be happening at that x value when the first derivative equals 0. You could have a maximum, you could have a minimum, or you could have a stationary inflection. Okay, so, but regardless, whichever one it is, regardless, the slope there equals 0. The slope is equal to 0. Okay, so all of these, your slope is equal to 0. So at the tangent, at a point, the slope is going to be 0. 0, 0, 0, 0. Okay, now if we have take the second derivative and set it equal to 0, when we find where the second derivative equals 0, that tells us where the function is changing shape. Okay, so here the second derivative equals 0. That means that the slope is not 0. Okay, so over here, the slope is not equal to 0. You can get these non-stationary inflections. So it's only changing shape. It's changing shape, but it's not flattening out and giving you a stationary inflection. Okay, so for these two right here, the slope is not equal to 0. So notice this one has a negative slope, this one has a positive slope. And you can tell whether you're going to have, concave down or concave up by looking at the values of the second derivative. So to the left of that x-intercept, this one would have, since it's concave down, it would have negative y values. And then to the right, it would have positive y values because it's concave up. Okay, so this would be an x-intercept on the second derivative. To the left of it, it's concave up, so it would have positive y values. And to the right of it, it would have negative y values. So we're going to practice making second derivatives in class next week. Okay, so this one, when the second derivative, when you set it equal to 0 and find those x points, you're going to get either a stationary inflection point or a non-stationary inflection. You get stationary inflection if both the first and the second derivative are equal to 0. And you get these non-stationary inflections. Notice non-stationary means it's still moving. So here it has a negative slope, here it has a positive slope. Okay, so here my slope is greater than 0. Oh, sorry, I said that wrong. Less than 0, that's the negative one. So my slope is less than 0. This one, my slope is greater than 0. So the first derivative would be less than 0. Here, the first derivative would be greater than 0. So we're going to do a bunch of work next week on this. Okay, so little summary. If a curve is concave down, the second derivative is less than 0. If a curve is concave up, the second derivative is greater than 0. So if the second derivative changes sign, then the second derivative is equal to 0. What? So the second derivative changes sign at x equals a, then the second, what does that mean? Then we have a stationary inflection point at a, and the non-stationary inflection. Okay, I think that summarizes what I set up here. So stationary inflection, the first derivative has to equal 0, and the second derivative equals 0. Okay, non-stationary inflection, the second derivative equals 0, but the first derivative does not equal 0. Okay, so these ones over here, again, the first derivative does not equal 0. Okay, because the slope right there does not equal 0. That's those ones. All right, so we will be practicing with this, with the second derivative, and using both the first and the second derivative to help us sketch functions next week. So without using a calculator, without using Desmos, we're going to be able to sketch some crazy functions just using their derivatives. See you next week.